Welcome to EMEE6002, Sustainability and Climate Change. Today's topic is wave energy. There are different types of wave energies. For example, in this diagram, we make use of the water wave in the oceans to generate electricity. It can be done by harvesting the kinetic energy in the water wave when it moves, and it can turn the turbines, just like the wind energy. Due to the gravitational force of the moon and sun, there are tidal effects. In the morning, when we have high tide, so the water will move from the sea to the river delta, and if we install a turbine at the entrance of the river delta, then we can harvest the energies of this wave to electricity by using a simple turbine and generator. In the evening, the water level in the sea will be lower. Then water will flow from the river delta back to the sea. So there will be reverse current, and then we can also harvest kinetic energies by this turbine. In this type of tidal energy generator, the turbine and generator will be submerged in the water, and there are maintenance and durability problems. So let's see this innovative design where we make use of an air chamber to capture the kinetic energy. Let's see this video.
The water of the oceans of the world is almost always in motion. Hardly ever interrupted, waves break at the coastlines, sometimes strong, sometimes weaker. There is an enormous energy potential that is available round the clock and free of charge. A potential that, if fully exploited, could satisfy 40% of the worldwide demand for power. This equals the output of 700 to 800 nuclear power stations. Voith Hydro WaveGen is developing technologies to convert this inexhaustible energy into electric power without the emission of harmful greenhouse gases. The operating principle of this wave power station is as simple as it is ingenious. An enclosed chamber has an opening beneath sea level, which allows water to flow from the sea to the chamber and back. The water level in the chamber rises and falls with the rhythm of the waves, and air is forced forwards and backwards through the turbine, connected to an upper opening in the chamber. As it is compressed and decompressed, the airflow has sufficient power to drive the Wells turbine. It is a feature of the Wells turbine, named after its inventor, that it is driven in the same direction by both forward and reverse airflow through the turbine. Even relatively low wave motions can generate enough airflow to keep the turbine moving and to generate energy. This is how easily energy can be generated with a wave power station, day and night, all year round, as long as there are waves. The world's first power station of this kind was put in service as early as November 2000 on the Scottish island of Islay, and has been feeding power to the grid ever since. Voith Hydro WaveGen is convinced of the commercial potential of wave energy. We are certain that our wave power stations can make a significant contribution to supplying the world with climate-friendly energy.
In this video, we can see we can make use of this sea wave going up and down that compress and decompress the air inside this chamber, so that the air can then pass through the turbine and generator. Comparing these two designs, one is the underwater wave turbine, and another is the air chamber tidal power plant. There are pros and cons. For the underwater type, the advantages is that the efficiency is higher and it can generate more electricity at any time. However, the disadvantages is that because the turbine and generators are underwater, so it's very hard to maintain. The disadvantages is that the turbine and generators are underwater. It is impossible for you to take away all the water from the sea. So you must ask a diver to dive into this underwater area to do the maintenance work. and therefore the maintenance is quite hard for this type of underwater plant. However, for the air chamber type, yes, it is easier to maintain because those turbine and generators are in the open air area. However, the efficiency is lower. Do you know why? Compared with water and air, which density is higher? If we compare the water flow and the air flow, the same equation will apply. Let us recall the equations of wind energies. Energy is equal to the constant multiplied by the efficiency multiplied by the area and the density of air. So if we put these equations into the wave conditions, so this density will be the water density, which is much higher than the air density. That's the reason why when we put the turbine under the water, where the water density is higher than the air density, the efficiency is much higher. Apart from submerging the turbine and generator under the water, there are many different types of water wave power plant. Let's see those designs.
A most promising energy solution today is to harness the kinetic power of the ocean waves and the flowing currents of sea or river. Many projects are underway and they claim to generate enough electrical energy for millions of homes without burning fossil fuels. These forces of nature are free, steady, and predictable. This video presents a new invention on various revolutionary fluid currents energy converter device by combining double-acting fluid pumping apparatuses and moving pontoon and racks to convert ocean waves or flowing currents into electricity. The two fundamental mechanical devices are the movable device and the fixed device. Double-acting piston pump. A piston is arranged to reciprocate as its piston rod is actuated by a float. When the float moves up as a rising wave passes, it pushes the piston upward and resulting dynamic flow of the fluid closes the left inlet by the ball and fluid pumped out through the center top outlet. At the same time, it causes fluid to flow through the right-hand inlet into the chamber. When the float moves down, it pulls the piston downward and partial vacuum generated at the left-hand inlet causes the top left ball to open and allow the fluid to flow in. At the same time, fluid pressure on the lower side of the piston becomes higher and it causes fluid to flow through the bottom channel into the right-hand chamber and pump out through the center top outlet. Based on the fundamental piston reciprocates working principle, many designs of energy converter can be configured. In this example, a submerged pump is operated to pump water to an elevated storage tank. Water from the storage tank is channeled to rotate a fluid motor or a turbine, which in turn rotates a generator to produce electricity. An air piston pump is disposed above the water level. The accumulator and flow control valve help to maintain a more constant airflow to drive a turbine and a generator. This design is integrated to operable both air and water piston pump. A T-shaped actuator bar is pivoted to the body of the pump such that when the float is pushed up and down by wave forces, the actuator bar oscillates about a pivot and, in turn, reciprocates the pistons. This actuator bar pump system uses the above single piston pump and a float pivoted to rise and fall with wave forces. Each pump body is configured to include two actuator T-bar piston pumps being arranged end-to-end with a sealed turbine disposed in between. The piston of two pumps is interconnected and is linked to a floating pontoon. Now a paddle is pivoted on the pontoon such that when the ocean undercurrents oscillate the paddle, it reciprocates two pistons to pump air and water in a double-acting manner. This design oscillates the actuator T-bar. On the top side of the rotary wheel, there is a crank pin or shaft that is located at a radius from the center of the rotary wheel. This piston rods of pumps are separately connected to the crankshaft through two link bars. The vertical rotary wheel has a plurality of peripheral aerofoil vanes and is partially submerged in a body of running water to catch the running currents and rotate. This design deploy in seabed. When water currents flow through the face of the pendulum member, a lifting force is generated and the pendulum member swings oscillate. This rotary wheel and piston pumps assembly is suspended from a boom on a mobile trailer. A plurality of one or more of the above piston pump configurations can be connected in a network. An ocean farm system comprises a number of network combinations of the above devices, be they the same, mixed, or different configurations being linked mechanically or electrically. This concept design is simple and unsophisticated, thus allowing us to harness huge unlimited renewable energy from our surrounding. If you can solve the power, you can solve almost anything.
I would like to show you this video to tell you that there's so many different designs, and there is no fixed rule and also no limit in the engine design. The limit is only by your imaginations. After watching so many different designs, let's do some mathematics and understand how to calculate the theoretical output of different hydropower. First step is the hydropower from the dam. Let's say we install a dam and then we can build a reservoir. So the height of this dam is a determining factor for the power output of this hydropower. Water will flow from the reservoir through the pipe and then turn the turbine, and the turbine can then generate electricity by the generator. The energy stored in the dam is in fact the potential energy of the water with this height. And we know that the potential energy is given by the density multiplied by the gravity multiplied by the height, where the density of water is 1000 kg per meter cube and the gravity is 9.8, take it 10 meters per second square, and the power of this hydropower will be given by the power is equal to the efficiency of the turbine multiplied by the density and the gravity and the height and multiplied by the flow of water from the dam. Because when we multiply by the flow rate by the density will be the mass per second flowing from the dam to the turbine. Let's say in this dam, the flow rate is 1 cubic meter per second. Water is flowing from the dam towards the turbine at the rate of 1 cubic meter per second. Then we put the number in these equations. The energy output will be 10 kilowatt, assuming the energy efficiency is say 100%. Okay, but usually we cannot achieve 100% efficiency, so you need to put a discount factor in the efficiency here. Apart from the energy from the dam, where we store the potential energy in this reservoir with a height of the water level, we can also convert the kinetic energy of a running river. Even though the river is at a horizontal level, there's not much potential difference from the upstream and the downstream. So when the water flows from the upstream to the downstream, even though they are in the same level, no potential difference. But because of the velocity of water flow, a kinetic energy will be built up. And the kinetic energy is given by these equations. Equals to half efficiency multiplied by the density multiplied by the Q, which is the flow rate, and then V squared. It can be divided by the characteristic equations. Energy is equals to half mv squared, and m is the mass. If you multiply the density by the flow rate, it will be the mass per second. And then if we have mass per second multiplied by V squared, so per second means energy per second, which means the power. Okay? So the power of this running water will be given by half efficiency density multiplied by the flow rate and then velocity of the water squared. But the flow rate is also equals to area multiplied by velocity. So the cross-section area of this cylinder of water will flow at the velocity v. So in 1 second, the volume is given by VA, and if we put this Q, this flow rate, into these equations, so power is equals to half efficiency multiplied by the density multiplied by area multiplied by the velocity cube, which is very familiar, right? This is also the equations of the wind energy. So actually, no matter this is wind energy or water energy, they share the same equations because this is the same theory of fluid dynamics. And the relationship between the velocity and the power is in the order of 3. So velocity to the power 3 is proportional to the power. If we plug the figures in this example into the equations, let's say we also have situations of 1 cubic. If we plug the figures in this example into the equations, we still have 1 cubic meters of water flowing in the water stream, and the efficiency is 100%. So we put those numbers into these equations, then we will get the number, which is 0.5 kilowatt. So if we compare the energy from the water dam that we just derived, which is 10 kilowatt per hour, so for the same flow rate, which is only 1 cubic meter per second, because in these equations there is a factor of gravity which is 9.8, almost 10. So the factor of gravitational force is dominant. And in these equations, the kinetic energies of a running stream, there is no gravitational force in this factor. So this factor of 10 gravitational force could not be found here. Instead, the velocity play a more important role. It's in the order of 3, v to the power 3. So if we can increase the water speed in this running water, because it's v to the power 3, then the power can be magnified. There are pros and cons of this river power. One of the advantages is that we don't need to spend a lot of money to build the dam, which is very costly. And also it can simplify the civil work. You can simply install the turbine in between the river, or you may have some pipe to divert water from the river from the upstream to the downstream. But however, energies from the river power is not that stable. Sometimes the water flow may be faster with more water after rainfall, or sometimes we may not have enough water in the river, and therefore this type of power may not be very reliable, and we need some backup supply such as battery storage or emergency generator and so on.